Hello everyone, my name is Satya, and in this set of videos we will be trying to understand the dynamics of rigid bodies. That is, we will be trying to learn how rigid bodies move or how they behave when they are displaced or when force is applied on them. So let us start by understanding what rigid bodies are. Now, according to our part of the course, we will rigid body will be defined as any body that resists change in deformation, as in it does not get deformed no matter what force is applied on it. That is, if a force is applied on this body, then if it is a rigid body, it means when we analyze the structure, the constituent particles of it before and after the force was applied, the position of the constituent particles are the exact same. So there is no change in that. However, in the real world, we know that there is no such truly rigid body, because on application of force, bodies do get deformed. Now, this is the reason why we have to learn about something called elasticity, which is the tendency of a body to return exactly to its initial state after it is deformed, no matter by how much. However, in this course, we will not be learning about elasticity, because we are not trying to learn the internal mechanics of the body on external application of force. We want to learn about the overall behavior, the overall displacement of a body in a particular direction or in a particular set of directions. So there are two main types of motion that are observed in rigid bodies, and one is translatory, that is, it moves in straight lines along any direction, and the other is rotatory, so in which the body is fixed at a point and a force applied on it causes it to rotate around, causes the parts of the body to rotate around that point. So there are two main notations for rotation that are important when we learn about rotatory motion. One is this. This means that there is a line that is perpendicular to the screen that is traveling towards you, the viewer of the video. And this means that there is a line that is perpendicular to the screen but traveling away from the viewer, away from you. So we consider this to be the axis of rotation. That is, it's a line that is perpendicular to your screen around which or about which this body is trying to rotate. So in these videos, we will mainly be talking about rotatory motion of a rigid body. So let us see what happens in rotational motion, mainly in pure rotational motion. So in pure rotational motion, in this case, in the case of this body, what happens is every constituent particle of that body travels in concentric circles around this axis. So this is the general form of pure rotational motion. So this basically helps us to summarize the rotational motion of any body into that of a disk. So if this moves in this way, then we can see that it follows a path similar to that of a disk. So let's look at rotational motion as just the motion of a disk. So if this is the disk and this is the center of the disk, so this is the axis of rotation. Let's say that the disk moves in an anti-clockwise manner, and let's say this is the radius of the disk. This is the radius of the disk. So we will see that at a particular time t0, this is the position of this radius. We will assume, let's say that at time t1, this radius vector reaches here, and at t2, it reaches here. So through this, we are basically trying to learn about two concepts. One is angular displacement and angular velocity. Angular displacement is basically the angle that this radius vector sweeps from its initial position at any given time. So the angular displacement between t0 and t1 is basically this much, angle theta and theta 1, and between t0 and t2 is basically this distance, which is theta 2. Now we can also calculate the angular velocity, which will just be the difference between angular displacements divided by the distance difference between the time intervals t1. So this should not surprise us, since this is very similar to a formula for linear velocity, which is just change in linear displacement divided by change in time. So similar to angular velocity, there is also a term called angular acceleration, which is denoted by alpha. So alpha is defined as the rate of change of angular velocity, that is omega 2 minus omega 1 divided by t2 minus t1. Now yeah, omega is also defined as rate of change of angular displacement, which is why it is theta 2 minus theta 1 divided by t2 minus t1. So angular acceleration, basically the implication of this is how much faster this disk spins. So by what rate the frequency of rotation has been changed. So since I spoke about frequency of rotation, it's also important to bring up one more thing. So we know that the angle of a circle in radians is 2 pi. That is, in degrees it's 360 degrees. So it is important to note that angular velocity is nothing but the frequency of rotation of this disk, which means that it is the number of times that a disk completes a full rotation every second. So that basically, a full rotation means it has completed 360 degrees in terms of angular displacement. So to get the per second value, we have to divide the total angle by a value t, which is the amount of time it takes to complete one rotation. So if we do this, we can get the angular frequency or the angular velocity, which is the same thing. So the other implication of the word angular velocity is the fact that it is the number of times the disk completes a full rotation every second. The angular acceleration is basically the rate of change of this frequency. So we can see that the formula that we are using for angular velocity and angular displacement are very similar to the formulae of linear velocity and linear displacement. So let us look at some of the similarities between linear motion and angular motion. Yeah, so the way to think about rotational motion in terms of linear motion is using the same disk. So if this is the disk, yeah, please excuse my circles. And this is the center of the circle and the axis of rotation. And this is the radius. We use the same angular displacement with respect to time, theta. And this is the direction of rotation. So we can imagine this to be a wheel. So if this wheel is moving in this direction, we know that this is actually corresponding to the length, the linear displacement of this wheel in the same period of time. So if this is the angular displacement, then this part of the circumference, that is this arc length, is actually how much the wheel covers in a straight line. So in mathematics, we are familiar with the formula that for a circle, if we know the angle between two radii, then the arc length x will be equal to r into theta, the radius into theta. Similarly here, if the linear displacement s is nothing but r into theta. Now this is not a cross product, don't worry. So it's in this case, it's theta is not a vector, so it's just scalar multiplication of the radius, and so we'll get another vector which is nothing but the linear displacement of the wheel. However, this brings about a very important question. Since I've been talking about theta not being a vector, but I have also been using omega and alpha, I've been depicting them as vectors. Are they really vectors? Well, yeah, they are vectors, and their direction is basically the direction of increase of theta. So since we know that the direction of rotation is this, That is also the angle of increase of theta, because the radius is, this line is basically is moving along this direction, thus increasing the angular displacement along this direction. So since we've spoken about all three of these, theta, omega and alpha, now we can also observe that their linear counterparts, angular displacement, it's linear displacement, angular velocity, it's linear velocity, and angular acceleration is linear acceleration. They can all be related to using this disk. So like I've spoken about the relation for theta and omega. For alpha, it's very similar. It's like the change in the arc length per unit time. So which is basically like defining this in terms of its linear representation. But yeah, you get the point. So basically they have three counterparts, and what is amazing is that in Newton's laws of motion, so S is equal to ut plus half at square, then v square is equal to u square plus 2as, and v is equal to u plus at. These three are the laws of motion that we are familiar with, and the amazing thing is that if we substitute the angular counterparts of these, all these equations turn out to be true. So I'll give you one example. So S, that is theta, I'm sorry, this should be S. So theta, this is not a vector, equals u omega naught, initial angular velocity, t plus half alpha t square. This is a valid equation. This works for rotational motion. Similarly, all of these work. And this basically poses the question, does this mean that any expression for the trajectory of a body that has been derived from Newton's second law, that is F equals ma, or F equals dp by dt, rate of change of momentum, anything that is derived from these, like the laws of motion are derived from these equations. They are just different interpretations of these equations. So does this observation mean that anything that is derived from this will hold true even in the angular world? Well, if that is true, then these equations should also have their angular counterparts, right, or angular analogs, right? So let's begin by seeing what we know here. So we know the angular counterpart of acceleration, that is alpha. Let us assume that the angular counterpart of F should be t, and then let's assume that m's counterpart is I. Now it's getting very obvious here, but let's bear with it. So yeah, let's also say that the p's counterpart is something called L, where t is the angular analog of force, I is the angular analog of mass, and L is the angular analog of momentum. So if we go to a new page here, if we assume these, then according to the respective analogous linear equations, the equations in linear motion, for F is equal to ma, we must get an equation that is of this kind. T is equal to I into alpha because of this correspondence, and we should also get tau is equal to rate of change of angular momentum, and angular momentum from the linear relation P is equal to mv we should also get something like angular momentum is equal to I into omega. Now the thing is, after observing all these, we came to know that all of these were true for rotational motion, and basically this gives us a lot of information. So this can help us to visualize rotational motion using what we know from linear motion. So we know that F equals ma, and one way to interpret this would be that acceleration can be measured for a particular force that is applied on a mass, and the analogous statement in rotational motion for a disk that is rotating would be that the change in angular acceleration can be measured using the amount of torque that is applied on it per unit analog of mass I. So let us actually know about the terms given, the names given to these values T, I and L. T is torque or moment of force. I is moment of inertia, and L is angular momentum or moment of momentum. So when we talk about these three, I will give you a brief description of these three, but we will discuss them in detail in the next few videos. Torque or the moment of force is basically vector r cross f. Moment of is basically a phrase. Moment of is basically a phrase that means vector r cross a particular value. So moment of force is vector r cross f. Angular momentum or moment of momentum is basically vector r cross momentum. Moment of inertia is a little unique. It's mr square, and we will learn the reason for it in a future video. So what I was trying to say here is that these set of relations give us an approximate idea about how an object behaves during rotation. It follows the same pattern that a body follows in linear motion. If we look at the properties of the body in terms of torque, angular momentum, moment of inertia and other analogues, instead of force, momentum and mass and so on. And the interesting thing is that the reason for the difference between these two worlds, the difference I mean is the factor that affects this rotation here is basically torque and not directly force, and in this case it's directly force. The reason for this difference is the dependence of the rotational motion on the point of application of force with respect to the axis of rotation. It's this distance that is causing all this difference. So in the next video, we will try to gain a clear understanding of torque, moment of inertia and angular momentum. See you there.